write this over here. Max of x and si, y and sj, distance x minus. Right, so here I had the minimum between the 2 points. This is the furthest between the 2 pair of points. So maybe you don't want any 2 points to be really far apart. So you want to minimize the compactness of the cluster. So these two have kind of very different properties. This one allows you to kind of get long kind of strings of points together and really doesn't want any 2 points to be far apart, where this one keeps all the clusters very compact. So your choice here is really a modeling choice in what you want the clusters to look like. Let me try and draw a picture here. So there are these kind of examples where you can get one point set that looks like this, and another point set that looks like this. And so if you are going to use this notion of distance in hierarchical clustering, what you might be able to get is two sets where one looks like this and the other one looks like this. You kind of get these points intertwined with each other. Because each point is close to some other point in this cluster. So there's always a pair which is going to be small here. So it's to the closest one. And whereas if you were to use, say, a lot of these other techniques, say the distance between the furthest pair, this is going to enforce that the clusters are going to be more well-rounded. Your result would probably be something kind of like this instead. And they may actually overlap in weird ways, but they're going to be more rounded. So it's not clear which one of these is better, and I've never seen a data set in practice that actually looks like this. I've seen lots of papers that have examples that look like this, and they say, my clustering algorithm can find this sort of clustering. Great. But I've never seen anything that looks anything close like this in practice. Maybe there's something that I haven't come across yet where this really is the right measure to use. So this sort of thing, and we'll mention this a little bit in the spectral section. We won't get too much. This sort of clustering is close to what you do in manifold learning, where you're trying to find these subspaces of points. And so you think there's actually a lower dimensional subspace, one that runs through here and the other one that runs like this, and you want to try and find these. And this was kind of a craze in machine learning 10 years ago. I'm not sure if people really use that much manifold learning anymore, but there were lots of cool pictures like this. There's this Swiss roll example, like a 3-dimensional version of that people were able to do. I have my doubts a little bit. All right, so this was talking about how do we find the closest two clusters in the set. And we've listed a bunch of these ways of measuring this. But this is only a subset of these possible ways. I left the screen up because I had a picture I wanted to show you. You probably don't care, but let's see. So, all right. So one other thing that's a little bit hard to draw, but so I'll just show this picture. You can do with hierarchical clustering before I take the screen down. Is you can also build these kind of tree structures. So this is why it's called hierarchical clustering, because you can kind of build this hierarchy on top of the clustering based on the order that you join the points together. The first 2 points together are joined together here. You kind of make this into one cluster. Then 4 and 5 are joined together. Then 1, 2, 3, and you kind of build up this hierarchy. It's like one of your trees. So this is very popular, for instance, when you're trying to understand the phylogeny of say, some different organisms, what was the evolutionary process where they split apart, or in some nomenclature, there's various areas where this is important. These pictures also become very useful. So it's a useful way of doing it. And so getting into how do you define close enough? Well, you can build this whole tree, and then you want to figure out how to kind of look at a subset of the tree. So do I stop here, or do I stop here? I can go all the way to the top. How do I choose to stop building? Okay, so this is maybe a useful picture. Okay, but let's now talk about how do we define if two clusters are close enough. So what were some of the ideas we had for how to define if these were close enough? So someone said something about the density. So you want the density to be below some threshold. Right, and the density could be defined something like, well, that's a good question. How do you define the density? You could look at the number of points over, say, the volume of the minimum enclosing ball, or there are other notions. You could look at a kernel density estimate on top of it and find the highest point. There are various notions of density you could use as well.
Standard deviation, can you use?
Yeah, so you could say, so you want the standard deviation to be less than some threshold. Right, so this is the average distance from the mean. This is kind of another way to define the density. Yeah.
Could we just say, we don't want a width increase of some threshold by adding a new point?
Yeah, right. So we have this notion of width. We're saying that the width of Si, Sj is going to be below some threshold. Right. So, yep.
We can also fix number of clusters. For a given data set, we can fix number of clusters.
Yeah. So we're going to fix K. So in general, this width can be replaced by any of these distances, right? So we could say just the distance of Si, Sj is less than some threshold, right? Okay. So in in 4 of these, I have this magical threshold. In this one, I don't have a threshold. I have a fixed K, which is equal to the number of clusters. Okay, so I've kind of told you what close enough means, kind of, but I haven't told you how to pick this threshold. And in this case, I have another problem. I have to pick this value K. There's some magic that needs to go on to choose this. And, well, maybe it's magic. Maybe this is really some sort of modeling choice. So with something like density, or maybe standard deviation, or one of these width, or one of these other things, you can depending on how you define these, maybe it's an intuitive notion that you can say this threshold really, really makes sense. So,
How do they decide on the threshold?
what?
How do they come up with the threshold? Like, how do they decide upon that figure?
Yeah, so that's a great question. So I don't have, so I actually don't have an answer for that. And anyone who tells you they do is probably lying. There's no magical way to always get this threshold.
Studying one, we can use standard deviation to get the threshold. Standard deviation of all the points, and then say, then define the threshold by 2 standard deviations.
Yeah, that's possible. You know, but if you have one outlier point that's way off there, it throws off the standard deviation of the whole point set. So, and maybe your points are, I don't know, there are various counterexamples you could say.
Could you do something like the threshold is the distance between 2 points within a set of node is less than the distance from that point to any other point, or another set having.
Yes. So you're right. You could do that. So that would be some possible choice. So you said. So maybe I'll try and write this up. So you say that the min distance between clusters is it? Is that what you want?
Yes,
Si, Sj. You want this to be less than.
the max difference between the things within a cluster.
The max over all I in our set K of min x y in Si x something like this. So this is the maximum distance between any 2 points in the cluster. So I look here, I have these points. It's the furthest 2 points here. And so then this is the distance between 2 clusters. They may not be the same cluster, and I want this to be so I want this property to hold, or I want this distance to be larger than this distance for any cluster. Yeah, that seems like it could be a very reasonable thing to say. Yeah.
I said this is something, for example, when I consider the natural environment, this is kind of the physical property of for example, the material that, for example, in shaping the crystals, the way that the crystal shape is the agglomeration, and how, for example, the crystal of some material is different from the crystal of another material is the difference between these thresholds. Because 2 molecules of the same type of one material in one distance could, for example, absorb each other and shape a, for example, cluster of other material have some other threshold, and so the shape of the crystal in 2 materials will be different. So these kind of properties of the material in the nature.
Yeah, so if you know, so often you can use a technique like this if you know some sort of some knowledge about your domain, and you can set some threshold based on some way of measuring, whether it's properties of your physical elements, and you know that the variation should be so far apart, you can set some sort of threshold. If not, you're kind of in trouble. So there are some things you can do. So I told you there's no answer to this. Well, there's kind of some there's some things people generally do. Okay, so that people, when you're trying to deal, anyone doing clustering has this issue. So either they magically choose some k ahead of time or some threshold and then they don't worry about it, or they'll do things like they will they'll try and draw pictures. So if your data is in 2D, or you can somehow embed it in 2D, and we'll talk about embedding techniques in a few weeks, then you can kind of see what the clusters look like, and if they look reasonable, okay. The difference between, say, if you had, so if your data look like this, and it happened to be in 2D, and you said this was one clustering, or you said, well, there are 4 clusterings. You know, both of these answers are reasonable. You know, it depends on what you're going for, which one you might want. But if you draw them, they both look reasonable. If you had said there was 16 clusterings and they're all a lot smaller, you probably weren't doing it right. Or if you had merged, if you said I want 3 things, and you had chosen these 3 clusters, this may not be right either. These 2 are pretty close to each other, and this one's pretty far away. So either you want 2 or 4 maybe. So drawing pictures is one way of doing it. There's this kind of this general technique called the elbow technique that often works fairly well. And it's drawing a picture, but this one requires some sort of embedding of the points. And you know, all the pictures I'm drawing are with points in 2D. Most times when people talk about clustering, they show points in 2D. Usually when you're trying to cluster data, if points are in 2D, you can just look at them and you're fine. Right? It's when you care about much higher dimensional points, or when you're actually dealing with sets, or you're dealing with other sorts of objects, that you can define a distance between them, but you don't know how to kind of represent them as points, or you don't want to lose the approximation error it takes to do that, say with something like one of these min-hashing techniques. So one thing you can do is you can say, so this will be the number of clusters. Okay, so this is going to increase, and this is going to be some sort of distance. It could be any one of these close enough members. Okay? So you hope that what's going to happen, and it's going to depend which way you do it, but as as you have more and more clusters, you're going to get a plot that kind of looks like this. Probably it looks like this. Hopefully, in most data, it'll look something like this. So to get more and more clusters, this distance is going to be smaller. This may not always be true, but then if you can draw a plot like this, and you can always compute this. It doesn't matter what your sets are. It doesn't matter what your choice of distance is. As you have, every time you have another iteration of this algorithm, you can compute some notion of close enough for the distance between the closest 2 clusters or something, and you can plot something. And then you want to say, well, this area here seems interesting. I've kind of started to level off. This is known as the elbow. It's like the elbow on your arm. And you want to say, well, this is a good number of clusters, or this is a good distance. Right? So this is a good threshold. So the threshold and the number of clusters in this way, if you see it this way, are really the same quantity if you draw this chart. Or they're not the same quantity, but they're related to each other in some way. Not all of these distances are actually going to be a monotone, but generally they're going to have some fairly smooth property in most cases. I think we'll mention a very different technique when we're talking about graphs and finding communities later on, called modularity. And this technique kind of has a natural stopping condition. It seems natural, but you can probably think of variants of it which seem just almost as reasonable. So some people say there's this modularity stopping condition which will answer this question, but I think there's also some modeling in there as well. We'll maybe talk about that in the graph part of class, towards the end of this semester. Okay, so right, so there are these. So there's lots of choices here. Okay, so we've covered. If you look at all the combinations, we've already covered probably a few hundred different clustering algorithms. So we're making pretty good headway. How long did that take? Like about an hour. We covered a few hundred clustering different algorithms, and people have written papers on all of these. So, and you know, if your data is kind of really, there's a good way to divide it into these sets. It probably won't matter too much what you use here. But there's some differences based on like the closest points, which sometimes called the single link clustering, versus say the furthest points. They're going to give you some tangible differences if you have these very specialized sorts of data. Okay, before I guess I want to mention the runtime of these techniques. So this is very general, but it's not necessarily very, very efficient. So how long does running this algorithm take? So assuming we have some notion of threshold, or as we're running, we're going to be calculating these distances anyway, so we can plot this, and then we can say when we get not too far past the elbow, we can stop. Right? So assume that we can answer the close enough using some technique like the elbow technique, or we have some predefined threshold. So then how long is this going to take? Let's say that we'll use the standard assumption that the input point set is of size n. So in terms of n, how is this going to scale? So n squared, you say exponentially. So it's not going to be, it's going to be in between those two. There may be some versions you can do in n squared, but it's not going to be exponential. It's going to be polynomial time to run this algorithm. Just to kind of optimize some function, you may need exponential time. So let's see, we're going to go through this while loop. So if we stopped when we only had one cluster left, okay, how many times would we have to go through the while loop? So, okay, when the first time, how many clusters are there? There are n clusters to start with, right? After the first time through the while loop, how many clusters are there? And then the second time through. Okay, so how many times we go through the while loop? So it's going to be n minus 1, right? So every time you lose one until there's one left, so they're going to be basically, I'll just say n. There's a linear number of times through. So there are n times through the while loop. Okay, and so I want to find the two clusters which are, find the two closest clusters. And let's assume that I can define close enough based on the closest two. Right? So I just need to find the closest two. So how do I define the closest two clusters? So let's say I'm at the point where there are still roughly n clusters, between n and n over 2 clusters. So I want to find the closest two. Yeah, so the naive way of doing this is going to be n choose 2, right? So I'm going to look at all pairs of clusters to calculate their distance. So that would be O of n squared. And so that means that I have n steps through. Each time I need to check all pairs. That means the whole algorithm, the total time is going to be O of n, which is the number of loops, times checking all pairs of clusters. So it's going to be n cubed. Okay, so there are constants I've missed in here, but as I get smaller numbers of clusters, right, I don't have to check as many pairs, right? So is this really n squared? Well, okay, let's just look at the first half the times through. So I go from n to n over 2 clusters. So those n over 2 steps are enough to get this O of n part here. Each of those times I have at least O of n, I have at least n over 2 clusters, and that's n over 2. I need to find all pairs of those, and there's going to be n over 4 roughly pairs. So I'm going to get, it's going to be at least n cubed over 8. And that's only the first half of the algorithm, but the second half should take less. But that's still n cubed. So it's still a pretty slow algorithm.
Not exactly. So you have previous information, but when you go for the next loop, so you can use that because you're only reducing 2 elements from the previous loop, right?
Good, good. Right, so when I go back and check the closest pair, most of the clusters have not changed. I already calculated that same distance before, right? So let's draw an example here. Let's say I have these. Let's say I have these clusters, and let me draw all of the pairs here. Okay, so I have all these pairs, and now I'm going to merge together 2 of these clusters, and now the new distances I need to calculate are here, here, and here. But all the old black lines, this one, and this one, I already calculated the previous round. Okay, so if I'm, and with the small example, you can't really see the savings, but if actually about n squared of the different distances, you've already pre-calculated. If you look at if there are n clusters, you go down to n minus 1 cluster as well. There are n minus 2 of them that all pairs you've already calculated. So you can pre-compute these. But you still need to find the smallest one. Right? You still need to find the closest pair. So we can't just say, let's just compute there are only O of n new distances from this one to each of the ones untouched. So I still need to spend at least O of n time here. But I don't always need to compute to spend the n squared here. So there's a day structure I can use called a priority queue. Which kind of keeps a set of elements in a sorted order. And I can always, I'm essentially keeping things sorted. I can remove things from the queue. I can put things in. I can find the smallest one in all of those operations in log n time for n points. Now I have n squared distances in here, but log of n squared is still log n asymptotically. And so that means if I use a priority queue, I need to update O of n distances at this step. But then the total time becomes O of n squared times log. Okay, so I can in general reduce it to n squared log n, but that's still going to be kind of slow if n is very big. If n is 1,000,000, then this becomes a trillion times log n times log of 1,000,000, which is probably another 20. So 20 trillion. I'd rather something that's going to run much faster. But if your data set's not too big, you can do a lot of different modeling here, and so some of these are useful. You have a lot of choices you can use. Okay. All right, so this was all I was going to say about hierarchical clustering. So I'm going to talk a little bit about case center and assignment-based clustering now, and then continue on to assignment-based clustering in the class on Wednesday. But does anyone have any questions on the hierarchical stuff? Okay, so all right, so so I want to talk about one algorithm in here. It's a very simple but very actually powerful algorithm. And if I run out of time, I'll start with it on Wednesday. The idea you have your input, okay, is going to be a set X, and you're also going to have some sort of distance defined. And if this is a metric, any metric then is going to have nice properties. So you're going to have a set and a distance, and your output is going to be actually now is going to be a set. It's going to be a set C of cluster centers. Okay, and the C is going to have some size k. If you don't know k, you can actually run the elbow method backwards to try and find a good k. So you're going to kind of go back the other direction now. And so you're going to have some function phi, phi of c, which applied to any point x in the set is going to find the min center in the set, x minus c. Okay, so this x is going to be an element of our input set. It doesn't need to be an element, but in general, well, sometimes it'll need to be an element. And so basically what this says is, I'm going to define a set of points C, or a set of objects C in the space, and I'm going to assign clusters. Now, Si, so Si is going to be the subset of X such that phi of C of X is equal to center C. Okay, so what does this look like? My input set is going to be, again, this set of points, because that's what I can draw. And then I'm going to define these three centers. Hopefully, they're going to be kind of close to my point sets. And then I can essentially think of drawing this Voronoi diagram between them, and all the points that are closer to this center than this center, or the other ones, are assigned within this cluster. Right, so now this becomes, if this is C1, then this is my set 1, this is C2, this is set 2, C3. So in assignment-based clustering, you always use this phi function where you map it to the closest center in your set. And these do not need to be elements of the set. Sometimes you restrict it so it is an element of your set. And in fact, we'll talk about now we'll only choose elements of the set. And then your clusters are defined automatically. So sometimes this is nice because it's pretty compact. You just need to represent the centers and not, and you don't actually need to like write down what cluster every point is in. This is a much more compact representation. And then given a new point, you can just look at the centers and find the closest one. Okay. So there are different variations of here, and so typically now you can actually define, before I couldn't really define what I was trying to optimize over. Now I want to optimize, so I want to optimize some sort of cost, and this is typically going to be something like, so one option is going to be so I'm going to look at every point, look at the distance to its center, and take the squared distance and take the sum of these. This is what's called k-means clustering. Note the squared here. For a long time, like in the 50s, there were papers written where they ran something that generated k-means clustering, and they thought it was the sum of the distances. And like, there's a strange history of confusing this. Like at some point, they looked at the center of the population of the U.S., and they thought they were computing an average, and they placed it in the wrong spot based on their definition, because people confused that this centroid is the sum of the square distances, not the sum of the distances. There's another thing called the K the k-median, and so the k-median clustering is just minimizing the sum of the distances instead of the sum of the squared distances. And there's some ways where this is actually much more robust, but this, we'll see, it's harder, at least in practice, to calculate than the k-means. So k-means, again, is not an algorithm, it's a thing that you're optimizing. And we'll talk about an algorithm on Wednesday. The thing I'll mention just now is actually what's called the k-center clustering, and it's just looking at the max. So I just want to I want to minimize the maximum distance between any point and its assigned center, right? So if I had a point, if I looked at all these distances, I want to find the largest distance, and that's what I want to minimize. This is called the k-center clustering. Okay, so k-center clustering is known to be NP-hard to actually solve exactly. So we're not going to completely optimize. In fact, it's known to be NP-hard to get better than a 2 approximation. So if you don't know what NP-hard means, it essentially means that under a lot of hypotheses of what we know about computing, it probably takes exponential time. There's technical definition, there's like, it means non-deterministic polynomial time, but we probably don't care so much what that is. But, so we don't know how to solve this exactly or do better than a 2 approximation, but we know how to get a 2 approximation, and in general it works much better than that. So we get a cost which is within a factor 2 of this cost. So I have 5 minutes to tell you the algorithm. And I'm going to try and write it right in here. So this algorithm is generally attributed to Gonzalez in 1985, so we'll call it the Gonzalez algorithm. You'll call it different things. So it's again a very simple algorithm. So we'll start with x equals to c1, and so this